Complex numbers, lesson 1, modulus and argument of a complex number. So I'm going to define a complex number, which I will call z. And z is going to be composed of a real part and an imaginary part. So z is equal to x plus iy. Now what we're going to do is we're going to draw the point that represents z on this argand diagram. So here are my axes. My x-axis, of course, is my real axis, and my y-axis is my imaginary axis. So my point x plus iy, let's place it over here. And what I'm going to do is draw a line from the origin to that point, a little bit like a vector. And what we know is, of course, that we have a right angle triangle, the base of which is x, and the height of which is y. And we can work out the length of that green line, a little bit like we would the length of a line representing a vector. And this is called the modulus of the complex number. It's the length of the line representing the vector of that complex number, or the distance, the direct distance between that complex number and the origin. So the modulus, as we would with vectors, is described as mod z, and it's the length of this line. Now, how do we calculate that? We use Pythagoras' theorem, so x squared plus y squared, and then square root this. So this is how we calculate the modulus of a complex number. Now, because the modulus of a complex number represents a distance, or the length of the line, it will always be positive. So mod z will always be greater than or equal to 0. Obviously, the value of the origin 0 would have a modulus of 0. One other interesting point that's worth mentioning here is if we identify the complex conjugate z star, which would be equal to x minus iy, and if we calculate z multiplied by z star, that's x plus iy multiplied by x minus iy. If you calculate this and do work this through yourself, you get an answer of x squared plus y squared, which of course is the square of the modulus, going back to this point here. So that tells us quite an interesting result, which is that z multiplied by z star is equal to the modulus of z all squared. So we're going to now look at a few examples. In each case, you need to sketch the complex number on the argand diagram and then calculate its modulus, simplifying where possible. So let's have a look at these examples. So number 1, z1 is equal to 3 plus 4i. So 3 plus 4i would look like that, and we need to work out the length of this line. So the modulus of z1 is obviously going to be the square root of 3 squared plus 4 squared, which is equal to 5. Now z2 is equal to negative 2. And the modulus of z2, we don't even need to use Pythagoras' theorem here, is simply going to equal 2. Now, z3, 4, subtract 2i, so that will take us down here. So there is z3, and the modulus of z3 is going to equal the square root of 4 squared plus 2 squared, ignore the negative, and this of course gives us root 20, or 2 root 5. And z4 is equal to 3i, so that would be up here. And again, there's no need to use Pythagoras' theorem here. The modulus of z4 is equal to 3. So think about the connection here with vectors and finding the magnitude or modulus of a vector. It's the same process. So what do we mean by the argument of a complex number? So here's our complex number z, which is equal to x plus iy. Now, as a side note, we quite often refer to the modulus as r, so the length of that line there. Now, the argument is the angle that is measured between the positive real axis and this line here representing the complex number. So we would define the argument of z as theta, and we would write arg z equals theta. Now, in order to ensure that any complex number can be defined uniquely, we define the principal argument so that theta, or arg z, has got to be between pi and minus pi. We typically use radians when we're dealing with complex numbers, but it is not wrong to give the argument in terms of degrees. It's just that you might be much more likely to work in terms of radians. Now, what does it actually mean for a complex number to have a negative argument? Well, let's look at the 4 quadrants. Now, if your complex number z, we'll call it z1, is here, then its argument will be this angle here, measured in an anti-clockwise direction. We'll call it theta 1. So arg of z1 equals theta 1. Now, if your complex number, we'll call it z2, is in this quadrant here, then its argument would be this angle here in yellow, which I'll call theta 2. So arg of z2 equals theta 2. Now, if your complex number, we'll call it z3, is here, then its argument is measured as this angle here, and it will be a negative value. So arg of z3 equals theta 3 in blue. And then finally, if your complex number is here, we'll call it z4. Its argument will be this angle here. We'll call it theta 4. So arg of z4 equals theta 4. And depending on where your complex number is in the argand diagram, that will affect the size and the sign of its argument, which is why sketching a diagram is absolutely fundamental, as you will see, when we're calculating an argument. Now, one last point of note, the origin has no defined argument. How would we define an angle? It would be impossible to define that uniquely. So we simply say the argument of 0 is undefined. So by now we should have an idea of how to calculate the argument of a complex number. So we're going to have a look at a few examples, and in each case we're going to find the principal argument of this complex number, giving our answer in exact form in radians, and if we can't give it in exact form, we will present our answer to 3 significant figures. So let's have a look at our examples. In each case, we need to sketch the complex number in question and then find its argument. So z1 is equal to 2 plus 2i, nice and simple, that's this number here. And its argument is this angle here, which we can very easily calculate using trigonometry. So we can say the argument of z1 is equal to arctan, or tan to the minus 1, of 2 over 2, which gives us an argument of pi by 4. Now, what about z2? That's equal to negative 1 plus root 3 I, so that's perhaps approximately there. And its argument is equal to this angle here, which means we need to work out the size of this angle, I'll call it alpha, and then subtract that from pi radians to get the obtuse larger blue angle. So we'll do this in stages. I might work up here for a little bit more space. So alpha is obviously equal to tan to the minus 1, or arctan, of root 3 over 1. I'm going to completely ignore negative signs here because that's going to cause me confusion. I'm going to end up with the wrong sort of angle. So arctan of root 3 over 1 gives me a value of pi by 3. So the argument of z2 is equal to pi, which of course would be the whole angle all the way up to here, subtract pi by 3, which gives us 2 pi by 3. Now, what about Z3? Z3 is in the bottom left-hand quadrant, -3 minus 4i, it's over here. So there it is, and there's its right-angled triangle there, and its argument will be this angle here. So if we were working out the size of this angle here, that would be negative pi. So the argument of Z3 will equal negative pi plus the value of this angle here, which I will call beta. And that then gives me the correct angle for the argument, which is this negative obtuse angle here. So again, I'm going to use trigonometry to work out the size of beta. I'm going to ignore any negative signs. I'm just going to think of a right angle triangle, which looks like this. There's an angle in that right angle triangle. Its base is 3 units, its height is 4 units. Think back to your year 9 trigonometry and working out the size of angle beta. You would never think about negative signs. You would simply do tan to the -1 or arctan of 4 over 3. And that gives you 0.9272 ... So we simply take that in radians over here, and negative pi plus that value gives us negative 2.214 ... which is negative 2.21 to 3 significant figures. So moving on to complex number 4, root 3 minus I. Well, that is probably going to be just about there. So there's Z4, and it's this angle here that we want to calculate. So again, we'll make a little bit of space to work out the answer to this. So number 4, we've got a triangle that looks like this. Root 3 here, 1 here. Again, ignore the signs completely, doesn't matter that it's a negative. And let's call this angle gamma. So we know that gamma is equal to arctan of 1 over root 3, which simply gives us pi by 6. But look at the direction, look at that yellow arrow. The argument of Z4 is going to equal negative pi by 6. Now, the last one, number 5, Z5 is equal to 2i. We can just about fit that on my diagram over here. So there's Z5, and its argument is simply 90 degrees, or obviously in radians, pi by 2. So if we'd had points on the major coordinate axes, on the y-axis or the imaginary axis, we've just seen the argument would be pi by 2. If we had a point that was here, can you see that in purple there on the real axis, that would have an argument of 0. A point here would have an argument of pi, and a point here would have an argument of negative pi by 2. Remember, we said that the principal argument of a complex number has got to lie between pi and negative pi. So this allows pi to be an argument, but not negative pi. So let's take a further look at our complex number z. Now, its modulus we're going to call r. So mod z is equal to r, and its argument we will label as theta. So the argument of z is equal to theta. Now, for simplicity, I've picked a point in the top right-hand quadrant. I didn't have to, it just makes the working look a little bit easier. Now, applying some very basic trigonometry, we can say that sine theta is equal to the opposite, y, divided by the hypotenuse, r. So I can rearrange that to tell me that y is equal to r multiplied by sine theta. And cos theta is equal to x over r. And again, we can rearrange that very simply to give us x equals r cos theta. Now, what can we do with these two results here? Well, we can substitute them back into here. So z, instead of x plus yi, we can write it as r cos theta plus r sine theta multiplied by I, and I'll put that bracket in for clarity. Now, quite often we factorise this, and for simplicity, write it as r bracket cos theta plus I sine theta, bringing the I before the sine theta to avoid any confusion. And this is known as the modulus argument form of a complex number. So we now have two ways of expressing a complex number. We have the Cartesian form of a complex number, where it's written in almost the format of coordinates, or like a vector, z equals x plus yi, and then here we have the mod arg, or modulus argument form of a complex number. As a little side note, the modulus argument form is sometimes also called the polar form of a complex number, and we would write z equals brackets r theta. So you define the complex number z by its modulus and its argument, almost like a pair of coordinates, and you'll be learning more about this when you learn about polar coordinates. Why they're called polar coordinates and why is this called the polar form? Well, the origin is referred to as a pole, and you are measuring the information, both the argument and the modulus, in relation to this origin. So we're going to have a look at a few examples. In each case, we are going to find the modulus and argument of these complex numbers, which are written in Cartesian form currently, and we're then going to convert them to modulus argument format. So here we go. Here are 5 examples. In each case, we're going to sketch these on this Argand diagram. So the first one is root 3 plus I, which would look a little bit like that. So there's z1. Now working out the modulus is always an easy thing to do, so we're just using Pythagoras' theorem. So that's going to be the square root of root 3 squared, which is 3, plus the square of 1, effectively. You've got 1i here, squared, which is just 1, so that gives us the root of 4, which of course is just 2. Remember, the modulus is always positive, it represents distance. Now, the argument of z1 is this angle here. Call it theta, if you can just about see that. So theta, we'll call it theta 1 to match z1. Theta 1 is equal to arctan, or tan to the minus 1, of 1 over root 3, which gives us pi by 6. So remember, the modulus argument form of a complex number is r bracket cos theta plus I sine theta, where r is equal to the modulus of z and theta is equal to the argument of z. So from here, we can say that z1 is equal to 2 bracket cos pi by 6 plus I sine pi by 6, and there's z1 written in its modulus argument form. So we have the Cartesian form over here, and then we have the modulus argument form, 2 different versions of the same complex number. And of course, if we evaluated 2 multiplied by cos pi by 6, we would get root 3 over here, and the same for the imaginary part as well. So what about z2? Let's draw this on. So negative 3 plus root 3i. So there it is. There is z2. Now its modulus, first of all, you will become very, very quick at calculating the modulus of a complex number. So that's 9 plus 3. So that is root 12, or 2 root 3. And its argument is this angle over here, which is pi subtract theta 2. So we need to make a little bit of space. I'll do that over here. Theta 2 is equal to tan to the minus 1, or arctan, of root 3 over 3. Again, ignore all negatives as you do this, please. And that is equal to pi by 6. So the obtuse angle, or the argument of z2 is equal to pi minus pi by 6, which is 5/6 pi. So z2 is equal to 2 root 3 bracket cos 5/6 pi plus I sine 5/6 pi. Now, what about z3? z3 is equal to negative 2 minus 2i. It's down here. And its argument is this angle over here, which is, of course, negative pi plus, we'll call it theta 3 over here. So first of all, its modulus. So the mod of z3 is simply equal to the square root of 2 squared plus 2 squared. So root 8 or 2 root 2. Now, what about its argument? I'm going to clear a bit of space over here, first of all, to calculate theta 3. So theta 3 is arctan of 2 over 2. Again, ignore all negatives, which gives me pi by 4. So the argument of z3 is equal to negative pi. Remember, that's if you go the whole way up to the negative real axis, plus this angle pi by 4, which gives me negative 3 pi by 4. So z3 in modulus argument form, we can just about squeeze it in, is 2 root 2 or root 8, doesn't really matter that much for the modulus there. Cos of negative 3 pi by 4, we must write in that negative, plus I sine negative 3 pi by 4. Okay, hopefully you can see that. So it must have the same angle here and here to truly be in modulus argument form. Now, example number 4, let's sketch it. 3 minus 2i, that's going to be over here. So its modulus is the root of 9 plus 4, or root 13, and its argument is going to be this angle here. We'll call it theta 4, but obviously expressed as a negative. So clearing a little bit of space for myself over here for part 4, we know that theta 4, just simply the size of the angle, is going to equal arctan of 2 over 3. Now, if I work that out, unfortunately, this is not a neat multiple of pi. I get 0.5880 ... So we'll round that to 0.588 to 3 significant figures. So the argument of Z4 is negative 0.588 because of the quadrant that it is placed in. So Z4, and I think I might just move it over here so that you can all see it, Z4 in mod arg form is root 13 cos of negative 0.588 plus I sine negative 0.588. And then we have Z4. Now the last one, very, very simple to actually see this one. We've got Z5, which is negative 4i, so that's down over here, Z5. So the modulus of Z5 is obviously equal to 4. And the argument of Z5 is negative pi by 2. So in modulus argument form, Z5 is equal to 4, bracket, cos negative pi by 2 plus I sine negative pi by 2. So in our last few examples, this time we're going to present numbers in modulus argument form, and we're going to read off their modulus and their argument. So this may sound quite easy. So let's have a look at the series of examples. So example number 1, Z1 is 5 bracket cos pi by 2 plus I sine pi by 2. Now, this has been expressed perfectly in modulus argument form. Remember, the angle has to be the same here. So this is really easy. We can simply read off that the modulus of Z1 is equal to 5 and the argument of Z1 is equal to pi by 2. Super easy. Now, number 2, a little bit more thinking required here. Z2 is equal to 3 cos pi by 4 minus I sine pi by 4. Now, that's a little bit more interesting, and there are a couple of tricks here that we can actually use to help us work this out. Now, why is it not currently in modulus argument form? Well, it's currently not in modulus argument form because there is a negative here, and there has to be a positive. Look at this original format here, there's always a positive there. There are loads of really nice ways of approaching this, but one way that we can do this is to remember that cos of negative x is exactly the same as cos of x. It's what we call an even function. Think about it, work it out in your calculator, look at the cosine graph. But sine of negative x is equal to negative sine x, because sine is what we call an odd function. So how does that help us here? Well, we can rewrite the part in the brackets as cos of negative pi by 4, because that would be exactly the same as cos of pi by 4, plus I sine negative pi by 4. Now think about why that works. It's going to work because sine of negative pi by 4 will equal negative sine pi by 4, and then that takes us up to the previous line over here. So we now have something that is written perfectly in modulus argument form, and we can read off that the modulus of z2 is equal to 3, and the argument of z2 is equal to negative pi by 4. That's just one way of approaching a question like this. You must be careful. It's very easy to be fooled by something like this and think it's already in modulus argument form when it isn't. And there will be another couple of examples that are also like this coming up. Now, example number 3. Can you spot why it's not in modulus argument form? Well, it's because it's got to have cos theta as the real part plus I sine theta as the complex part, and this appears to be the other way around. So what can we do? Again, there are so many different ways of approaching this, and really interesting if you can come up with some other ways of doing it. One way is to actually simply rewrite this in its Cartesian form, so that's root 3 over 2 plus a half of I. Now, where would I go from there? I would very definitely sketch this in an Argand diagram. And look how quickly I'm sketching. This does not need to be something we spend ages over. Root 3 over 2 is about there-ish. A half is about there. So that means this point would look like that. So that distance there is root 3 over 2. That's half. There's my right angle triangle. Now, what is the modulus of z3 equal to? Well, it's the square root of root 3 over 2 squared plus a half squared, which you will find out comes to 1. So actually, we could have seen the modulus of this quite easily from the beginning. But the argument we can then see is this angle here, theta. So theta is equal to arctan, or tan to the minus 1, of a half over root 3 over 2, which comes to a value of pi by 6. So the argument of z3 is equal to pi by 6, and we can establish all this information just from its Cartesian format. So that means to be in true mod arg form, z3 would equal 1, which we don't need to write down, cos pi by 3 plus I sine pi by 3. Done. So example 4, what's the problem here? Well, have a look again at the start of this. Remember, to be in true mod arg form, we have to be expressed like this. And the modulus of your complex number, mod z, which equals r, must be greater than or equal to 0. It cannot be a negative number. So here's how we're going to approach this again. We're going to expand this bracket, so we get negative 2 cos pi by 6 minus 2I sine pi by 6. And we're going to work these out so we get z4 in its Cartesian form. So this is negative root 3 minus I. And at that point there, it then becomes a very easy problem to solve. Again, a quick sketch on a set of argand diagram axes. So negative root 3 minus I is going to be in this quadrant over here. That measurement there is root 3, that measurement there is 1. And of course the argument would be this angle over here. So if I call this theta, first of all, let's work out what theta is. So theta is equal to arctan, or tan to the minus 1, of 1 over root 3. So that comes to a value of pi by 6. So this angle here, of course, remember we need to work out negative pi plus the value of theta to get the correct argument. So the argument of Z4 is equal to negative pi plus that value pi by 6, which is negative 5 pi by 6. And of course what we haven't done is work out the actual modulus of Z4, and you will notice it's equal to 2. So we could actually glean that information from the starting point, but of course we had to work through the process to get the correct value of the argument. So this gives me Z4 is equal to 2 bracket cos negative 5 pi by 6 plus I sine negative 5 pi by 6. So let's look at the last example. Have you spotted why it's not in true modulus argument form? Well, to be in true modulus argument form, we need to make sure that the value of r is the same for both parts, and it's not here because we've got 2 here and we don't have that over here. So let's switch straight away into Cartesian form, and we get negative root 2 plus I multiplied by root 2 over 2. So here's my sketch of my Cartesian axes, just a rough sketch. Negative root 2 might be about here, root 2 over 2, remember this is not to scale, might be about here. So my angle that I'm looking for the argument is over here, so we need to work out theta first of all. So theta is equal to arctan, or tan to the minus 1, of root 2 over 2 divided by root 2. Again, ignore the negative sign here. And you don't get a nice angle here in terms of pi. We get just a decimal value in terms of radians there. And of course, the argument of Z5 is then equal to pi minus 0.4636. So we get the obtuse angle, which is then equal to 2.6779, or 2.68 radians to 3 significant figures. Now, what about the modulus? Always easier to work out. The modulus is the square root of root 2 squared, which is 2. Again, ignore all negative signs. And then when you square this, of course, you get a half. So that then gives me the root of 5 over 2. You can rationalise the denominator if you want to. It doesn't really make it that much less complex of a number. So Z5 is equal to the square root of 5 over 2 cos of 2.68 radians plus I sine 2.68 radians. You can put a little C for circular measure to indicate you're using radians there if you like. So remember, if you are trying to find the modulus and argument of a number that hasn't quite been written correctly in modulus argument form, convert to Cartesian form, sketch the diagram, recalculate the modulus and the argument, and then put it back together in modulus argument form properly. So that's a quick summary of what we've just looked at in the last few examples.